Some of the issues that we face with electricity distribution is because it's of a dynamic nature. There's a curve that we follow during the day called the load profile. We expect to see a peak early morning when people get up for their breakfast, and we expect to see a peak at early evening when people come home, they switch on their lights, they switch on their appliances. One of the benefits of energy storage is that we can store energy in the quiet periods in between those peaks, and then we can use it to discharge and support the network at those times. You need to have a lot of generation that's on demand, ready to generate to cater for that load when it comes on. That whole generation is called spinning reserve. So the national grid, when you look at the entire country, they all cater for those peaks by having power stations that are standing ready and waiting. They still need a specific period of time to actually start up. But what you can do with electrical energy storage, and especially batteries, is that you can discharge them very, very quickly.
Batteries on the grid can actually solve a whole collection of different problems. Sometimes you're needing to take wind energy while it's blowing, but you don't need the energy at that moment, so you can store it and put it out later. Sometimes you're constrained about how much power you can put down a transformer or a distribution wire. And so being able to store the energy when your demands are low and put it back out onto the network when demands are high really helps stabilize temperatures, which leads to longer life of equipment. You can smooth out a lot of different variations.
There are other requirements placed on the DNO which are about voltage control, about making sure that the volts don't go too high, about making sure that the volts don't go too low, and that the power quality is stable. Energy storage can support us in maintaining those tight voltage and power quality tolerances. So in CLNR, the plan for storage was to act as one of the tools in our toolbox for controlling network voltage and power flow. So we're fortunate on CLNR to be able to deploy 6 different battery types on the network. The primary reason for having 6 different batteries at various scales, some being large, some being medium and some being small, is that we can fit them across the entire range of our distribution network. Right from the very top, where our source injection comes in, through primary transformers, and being fitted deeper and deeper and deeper into the electricity distribution network.
If I can caricature our networks, we tend to see voltage problems out on the long, stringy rural networks, and we tend to see overload problems on the short, fat urban networks, which is why within the CLNR programme we've gone to a dense urban network out of Rice-Carr and a very sparse rural network out of Denwick.
Northern Powergrid has selected 6 sites, Rice-Carr being the largest of them. There's 5 smaller sites. Northern Powergrid selected these 6 sites because taken together as a whole, they represent about 80% of all of the UK's electrical grid.
Our building blocks are the same at every site in this country, so even though the sites themselves are quite different and some of the physical exteriors are different, most of the component building blocks are all the same.
Each site presented its own problems, mostly with physical constraints, because we were trying to get the batteries located directly next to the loads into the small neighborhoods.
Many of the sites were quite space constrained, so there are some challenges in installing them. We had to get a crane in here to actually, these battery containers ship at about 50,000 pounds each, and when fully loaded are actually above 100,000 pounds. So getting the equipment in here to move these around on a relatively small footprint was a bit of a challenge.
Here at Rice-Carr, we have the largest system of 2 battery containers and 1 central inverter. The rating of the system is 2.5 megawatts source and sink and 5 megawatt hours. So we can push and pull quite a bit of power onto the mains. 2.5 megawatts is approximately enough to drive 500 very large homes for several hours.
In our urban test cell, at 6,000 volts, is traditionally at the lower end of our distribution network voltage level, which means that the currents are relatively high. So the energy storage in this particular instance is enabling us to limit the amount of current being passed through that transformer by supporting it thermally. Traditionally on our rural networks, we feed electricity exactly the same from a primary substation. However, it feeds over a much greater distance, predominantly by overhead lines. Our limiting factor on the end of those overhead lines isn't power flow anymore. It's all about controlling the voltage and keeping it within some tight statutory limits.
The Wooler sites, they're smaller units. Each of those units could probably run maybe somewhere between 30 to 50 houses for a day.
We're up here at Wooler, which is in Northumberland. Today we've been delivering the equipment onto site, which is part of the electrical energy storage system.
One of the problems that we have in a village like Wooler is the infrastructure is very old, and it's very expensive to excavate streets to put in new distribution feeders. And what we're hoping this equipment will be able to do is to take some of the load off of those aging feeders and transformers and prolong the life remaining in those system components.
Typical demand profile on a rural network might be entirely different from that in an urban network. You're looking at predominantly off-gas network where people will use heating and lighting always by electricity. So we're looking at seeing what benefits energy storage can have us in catering for the swings that are generated by that demand shift. One of the low carbon technologies that has become prevalent, and we see it everywhere now on all our rooftops, is the penetration of photovoltaic cells on people's roofs. Now, one of the impacts in that is that photovoltaic cells began to distribute themselves in a cluster, and some of those clusters were causing us a great amount of concern. One of our specific sites where we're looking at the impact of solar PV on the electricity network is at Maltby, a site just outside Sheffield. One of the benefits in having the energy storage system there is about capturing some of that solar PV that's being generated during the daytime and discharging it during the evening. Battery technology isn't new to us in the electricity distribution network. However, grid-scale battery is completely new. It is innovative. It is only being trialled amongst a very small group of projects, and the CLNR project being one of them.
We've already seen from the academic papers and the modelling that's been done, so before even we put the batteries in place, we were looking at what might happen and how we might use these batteries, particularly how we might use a battery instead of demand-side response or in conjunction with demand-side response, so customers doing things to help us out with a particular network constraint. So we'll get to see if the models were accurate or not, and some more besides. So we're going to see some real needles moving on some real substations as the batteries are moved on, switched on and off, and compared to the academic models for the sort of experience we had predicted from the network.
Northern Powergrid created a very nice research project when they built this. The 6 different sites, the 3 different power scales, the different geographies. They'll be able to prove out a lot of interesting ideas with this.
We set out quite deliberately to make this apply to at least 80% of GB networks. Personally, I think it's almost all of it, because amps and volts are amps and volts. It will apply to most places. So we set out to cover quite a wide range, and we will roll that out. Just to illustrate the point, the 2 test networks we've chosen, Ricecar and Denick, that to me as an engineer, I know that the precise voltage doesn't matter. It doesn't matter whether it's 6 kV or 11 kV or 20 kV. It's all the same. But we very deliberately said, okay, we'll do one at 6 kV and one at 20 kV, so we've got the whole range. So when we go out, we can say, look guys, we've made it work here, and we've made it work there. It will cover everything in the middle. Similarly, we've gone for a quite dense urban network and a quite sparse rural network, because the maths is the same, the physics is the same solution should apply in both. But again, we can go to people and say, yeah, look, it works here, it works there, it'll work anywhere else that you've got.
Battery systems are a new technology, and this is the first project of its kind in the UK. And especially the complexity of doing 6 sites simultaneously of 3 different power scales. It's been interesting.
There are many lessons to be learned from what we've been through, and there's many lessons to be learned from what we can share with others.
We've always been of the view that if we're taking public money for this, because customers are paying for this, there's a separate sum that we're taking out of customers' bills for this. We've always been of the view, if we're taking public money for it, we have to put that information back out there.
There have been groups that have been started up. There have been forum groups on energy storage where we're beginning to share the knowledge that we've achieved from installing battery storage across a number of range of our locations with others, so it will assist them and the industry as a whole.
I don't like talking about a smart grid because it infers that the one we've got is dumb, and I don't believe that's the case. I like to talk about smarter grids because I think we're on a path. I think we're on a path that's been going for 10 or 20 years and is going to keep going as long as people need electricity. To me, adding smartness to a grid, it's about adding a layer of intelligence and communication and control. It's a bit like a road junction. You can take the hard civil asset of the roads and the junction themselves, take a roundabout, for example, and then you can put traffic lights on it. So to improve the flow, you don't rebuild the roundabout. You put some wiring in, you put some signals in. And by adding that layer of intelligence, you get more through the roundabouts.
What we've been trialling here and what we've been developing is this new active network management system that we call GUS. We have a number of new novel network technologies that have been deployed across the network that act as levers that it can pull. Okay, so effectively tools in its toolbox. Batteries and energy storage as a whole is one of those tools.
This is pretty ambitious, and I think where the customer-led network revolution really does distinguish itself from what's gone before, it's the integration of that storage with the other technical solutions of voltage control or real-time thermal rating, along with the customer solutions of demand-side response. So it's bringing it all together and using energy storage as part of the mix in terms of being a solution for the future.
One of the benefits in the new technology that we have is in the fact that it has intelligence that's been built into it. It has an awful lot of monitoring that's been built into it, and it has an awful lot of communications that are built into it that enable us to control it from afar, to understand what the battery system is doing, to maintain it from afar, and then to understand and respond to it in the fashion in which we need to. We think here that we're developing the most advanced active network management system that there is available.
I'm not sure what challenges customers are going to throw up at us in future. I don't know whether it's going to be an issue of big demand with things like electric vehicles and heat pumps. I don't know if it's going to be an issue of a lot of generation, solar panels, wind generation of various sizes. I do know that it boils down to volts and amps, and a lot of people worry about generation and voltage rise. Now, I don't think voltage rise is necessarily a problem. I think it's voltage swing. It's the change. It's the change from top to bottom. You know, how hard are you stretching the network, pulling it in both directions? That's what really gives people an issue. That's the challenge for the power systems engineer.
Being able to put storage on the grid is absolutely essential for future green energy and also absolutely essential for smart grid application. It allows you to push and pull power at different times of the day, whenever you have it, whenever you need it. It allows you to stabilize weak and unsteady parts of the mains. It's really, really important.
The core learning to come out of the installation of electrical energy storage is firstly about the technology itself, as in how effective. A core factor is how much headroom do these devices release, and what is the cost of releasing that headroom. But the other part, which is key about the customer-led network revolution, is the impact it has on customers.
This project is called the Customer-Led Network Revolution for a reason. It's because it's to do with enabling customers to make the low-carbon transition. So what we have to make sure we do is make sure that we consult the stakeholders, consult those people and organisations who want to make the low-carbon transition, and make sure we're listening to them and keeping up with their changing needs, and making sure that the project really is focused on delivery and facilitation of those customers and what they want to achieve.
The great hope is that this becomes a business as usual activity, and that storage units are used, but they'll only ever be used where there is a cost benefit and where they're appropriate to do so, appropriate and safe to do so.
One of the benefits for CLNR means that the normal person on the street who's fed by our electricity distribution network shouldn't see any change in the delivery of electricity, shouldn't see any shift in their power quality, shouldn't see any shift in the voltages that are delivered to their premises.
You're probably never going to notice that the fact that batteries have been connected in your neighborhood or in your factory or in your basement. They're just going to be part of the network the same way that the copper wires are part of the network. You don't pay attention to it.